Great. Another Thursday seminar live here with Ruth and Sophia. Long time that we know each other from different types of interactions. I've visited her in Portugal in the labs. Now I know she's in Germany, and we will have also common collaborators soon working in the lab, and we'll see each other also in UCNC in Belgium next month. Looking forward to catch up. And talking about catching up, Ruth is bringing today a very interesting seminar um, that merges a couple of hot topics, right? Internet of Things, Edge Cloud Continuum. We hear a lot about this. What is this continuum of Edge and Cloud? And of course, energy efficiency and resiliency, so relevant properties of any networked system. As usual, Ruth, I am very informal, so I'm not going to read your extensive bios. Our students and watchers can read and also follow your links, your publications, follow you, connect with you over LinkedIn. So with that, I will stop my screen sharing. I will pass you so that you can present, usually around 40 minutes, and then we will chat, and I will pick some questions from the class and also from our live participants over YouTube. Okay. So
Okay,
thank you.
thank you. So hi everybody, and Christian, thank you again for the invitation. It is really also a pleasure to speak again with you, and I'm really happy that we are going to meet each other again in or have this chance in Antwerp, because after COVID, as we all know, a lot right happened. So as Christine explained, and let me see if I can move my slides, right? I'm going to today speak about this so-called edge to cloud orchestration. But before that, I have a quick, I hope, introduction. So Christian didn't introduce me. I would like more to introduce what I'm doing in Germany right now. So you see here my background, and I'm not going over that. What is important, I think, for the seminar is for you to know that my background, technical background, is on packet-based networking. So in the past, I've worked on things like quality of service, IPv6, but I've also worked on MAC layer design, on high-speed networking, and then also on wireless. And since 2019, I moved to an institute in Germany called Fortis. We are in Munich, so in the southern part of Germany, to develop a new team focused on industrial IoT. So technically, where we focus is on next generation industrial IoT applications. And our research is focused on the development of networking architectures and protocols, because that's where my background and I think my best contribution can be, and also on computational architectures. So in a sense, this is a mixed team, so interdisciplinary team. It means that my team has, as researchers, people that come with a background from networking, like me, but also people that have a background more focused in IoT, for instance, with some knowledge on semantic technologies and some knowledge, for instance, in AI, not on developing new AI models, but actually on AI engineering, in particular for edge computing. So the institute where I am, Fortis, you have here information. Okay, so is a software-oriented institute. So this means software engineering-oriented institute. We have a number of teams. So we call those teams competence fields. And each team, let's say, the teams are aggregated into three clusters. One focuses on software engineering, the other focus on industrial or intelligent infrastructures, and the third focus on robust AI. And so this means that, as said, there's also this interdisciplinary notion among me and my colleagues. And let me give you also a quick view on what we do and how we perceive IoT, because that is important to understand our notions of edge, cloud, continuum, right? So everybody's speaking about this. So we have a vision for that. So in the industrial IoT team, our vision is that in order to enable next generation IoT, and this next generation IoT will is comprising and will comprise mobile devices, so heavily will comprise mobile devices, but also, as we know, very, very small embedded devices. But it also involves people and it involves AI, so cyber physical objects with cognitive capability. And in order to, so imagine all these devices and cyber physical systems interconnected and also people and interconnected by a system of networks. And that system needs to be a bit more clever than what we have today on the internet. And so the vision of my team is that we think we should rethink and redesign, up to some point, of course, some of the infrastructures that we have for IoT. And that redesign is based on considering a joint design of networking and computation. So the way we work is that we do research, of course, similar to what possibly you do with Christian's group. And then our outcome is normally based on scientific publications, but also, and I think this is relevant, open source software. So there's a link here, okay, that you can check with some of our most relevant open source software. Normally, we have some demonstrators for the edge, so that's where we are focused. Now, really going into the seminar. So today what I bring you is some information about what is this edge to cloud continuum. And then I'm going to bring you an example based on an European project called Codeco on how we perceive this orchestration. What does this mean? What are we using in terms of technologies? And then I have created also a few other parts on the seminar. Okay, so one relates to give you some information about use cases. So where do we need these? Where are these environments that are a bit more variable than the ones we have today on the internet? And I bring also some information about how you can experiment with this project. So maybe this is interesting because we are developing a bunch of open source software with a number of companies and academic partners in Europe. And maybe this is interesting also for you as students. So, but let's start by the beginning. So in order to explain to you my view on Edge Cloud Continuum, we need to go back and to think about Internet of Things, but also to think about that now we call it Internet of Things, but in fact, it's the internet, right? So the Internet of Things, it's basically the internet since its beginning, so since DARPANET. So it's just that it has evolved and evolved and evolved. It is a complex system, but now it interconnects a lot more things. And most of the traffic is on the edge, on the fringes of the network. So the internet, as it was designed, there's a principle on which it is based called the end-to-end principle, which basically says that the intelligence is on the edge. So the intelligence is really on the system. There's nothing intelligent in the middle. We just have a bunch of dumb transporters. And that is the network. That's what we call infrastructure or the network. But the issue is that with these new interconnections that we have now to the internet, okay, so with our smartphones or with sensors, also with more clever sensors that can already think and react, also with satellites, the notion of edge, of what is the edge on the internet, is not anymore on the fringes. We cannot say anymore that we really have applications on the fringes and or on the extremes of the internet. And so this means that there is now the needs, and a lot of people across the world are thinking about how to adapt to the needs that we have in new applications. So a fact is that this end-to-end principle is anyway changing because we have also other things on the network. We have programmable devices. We have new ways to do computation, so not necessarily just on the extremes of the network, but actually in routers already. We can do caching in routers. And so this all changes the way we process information, but also that we compute the applications. And so where are we today in terms of Internet of Things? So that's sort of how the internet is evolving. So you have here two figures that show a little bit the confusion that we have today on the internet. So on the left-hand side, you see that we think about the internet as this complex system. So we all know, of course, that there are differences in capillarity, and we still have, let's say, areas that are so rural, peri-rural, that are very isolated with lack of internet access. We have some lack of telecommunications still, so not necessarily on rural areas. So I'm here in Munich, but if I go to a lake 80 kilometers away, closer to the Alps, then my 4G access disappears. So this is basically in urban areas, we know we have dense support, and outside it's still a problem. And we have something new, which is spontaneous communication. So today on the internet, we also have the possibility to create infrastructures on the fly to with a specific purpose, for instance, emergency communications for health or after a natural disaster. So today these are functions that we have and that we can support on the internet. So on the right hand side, that's the example that you have. So very stable telco-based infrastructures, and then mobile, okay, integrating satellites, UAVs, and so on, but also spontaneous communications. And the mobile devices that we have today, they are also changing. So they can do storage. So our smartphones, they can do this, as you know, they can do computing. They can reason up to some point. So we can have reasoners there, and we have a bunch of different networking technologies that are supported. So this is becoming increasing complex. And so the idea of explaining this is to tell you it's not manageable anymore just based on human configuration. So it's not actually just a matter of, for instance, ensuring that all our access points are well placed, etc., or that our node Bs or our RAN areas are well configured. In fact, the internet, as it is evolving, requires some facilitation of intelligence so that it can easily adapt to new situations. So that is, let's say, the perspective of the internet, right? And then on the Internet of Things, we have, of course, the networking part, but we have the systems. We have the systems that process data, and that gives us clever results about data, so based on data sources. And so on this slide, what I bring you is a set of core principles or aspects that any IoT system has. And the issue is that today we have over 600 proprietary IoT systems. So it is very hard to handle the interconnection of thousands or hundreds of sensors already, for instance, in manufacturing, in factories, or even, for instance, in aeronautics, which is another example of industrial IoT. A plane has already hundreds of sensors, and normally they would be connected via Ethernet or via some other fixed form, and that is being changed, and people are using more and more wireless and cellular network technologies. So that's just the part. That's what you see here represented as connectivity. What we also have on IoT system are the interfaces to the user, so the human machine interfaces. And we have the data sources, which can be our sensors, but can also be people, and can also be already, as you know, objects or cyber physical systems, or really just softwareized agents, such as an AI agent. So a bot, a chatbot, can be a data source for IoT. And then, of course, we have parts or systems or applications that process the data, because that's the important part in IoT, and that store that data in a way that is secure. We hope that it ensures privacy, and also one thing that is becoming more and more important is to ensure sovereignty, which means that the data can only be used by, let's say, their own shareholders or stakeholders, and also that the data is, let's say, adequately certified or regulated within a specific region worldwide. So that all is IoT. Also, so when we speak about Internet of Things, as said, the thing itself is a semantic abstraction. So it's not an object, it's actually a description that we do today that describes the object. So the thing embodies, let's say, a description. So embodies the description of an object. Okay, but it can also embody the description of human behavior. For instance, I'm going outside and jogging, and therefore I run at some speed, okay, or I stop. Now I am stopped. So that information can be seen as being sent from a data source, and it is relevant for some applications. So this is Internet of Things, but we spoke about edge to cloud orchestration. So we are speaking about the internet, the transport part, the edges. So what is this edge to cloud continuum, and why are people calling it edge to cloud continuum and not just internet? So when we speak about the internet, we focus more really on the infrastructure aspects, so on the transport of information. And when we speak about edge and cloud, we focus on the data processing and on the data storage. So on the improvement of processes, on the improvement of the performance of applications that we are using in some specific use cases or domains, for instance, in health or in manufacturing. And so today, okay, so there are different, of course, different terminologies for edge. You will hear about deep edge, far edge, micro edge, nano edge. Okay, so today what I bring you is sort of a perspective, okay? There are others, but the perspective that we are pursuing heavily in Europe, okay, on the differences, let's say, of what is far edge and near edge. And I'll explain also why we need to have that difference, okay? But the edge to cloud continuum is basically a representation, okay, of all the computation and networking management and networking control that we need to do to ensure that the data is adequately processed and that we have the performance that we need for some application from edge to cloud. And why from edge to cloud? And where is the edge? So the edge is closer to the end user, to us. From edge to cloud, because today most of the applications, as you will see in some examples that I bring, they are not anymore stored or computed just on the cloud. And the reason for that may have to do with costs, but has also, it's sort of a process, has also to do with the technological evolution that we have today, where virtualization has gained a new space on internet and on the development of applications, and where new application architectures, so applications that are more modular, not anymore monoblocking, started to emerge. And also, finally, due to the type of hardware that we have and the capability to have, let's say, more open hardware, more programmable hardware. So the representation that you have here is a potential representation, okay, of what is far edge and near edge. And basically, you see here the human and IoT interfaces close to the real world, so close to the people. We are data sources. Other data sources are cars or other vehicles, so the so-called vehicle to everything, cameras, them sensors like temperature sensors, and other types of sensors. The far edge today is connected to all the sensors that we as end users use close or in the real world. So they are not normally controlled by an operator because the operator does not have the reach to control them. But they are extremely important to the internet because that's where the data sources are. Okay. So to give an example, imagine your home, okay, in the home automation, and then you have your uh, network terminator, okay, and your access point co-located with a local router. And then you have a bunch of smart things in your home, measuring a lot of things, Alexa, and controlling the light. So all that is the far edge. So your operator reaches the network terminator that he places close to your door. But beyond that, there's no control. And in fact, all the data is there. So we call that the far edge. In a factory, we call the far edge, for instance, involves all the equipment that brings data to the system and normally relates with what we call a shop floor or could be a warehouse. Again, there is no control of the operator there. So in this design, that's where you see the far edge, okay, simplified design, and the near edge is actually the area that the operator controls. So a very known model, okay, that you possibly know of for an ear edge is ETSI-MEC. Okay, so this means that what we do today, and let me show you another picture so that I can give another example. You have here a similar representation, just a little bit more detail. On the left-hand side, you have the far edge. So here, imagine this is for industrial IoT. Okay, so imagine a factory, and then there's a shop floor where we have conveyor belts, robotic arms, etc. And maybe we also have other locations like a warehouse where we have automated guided vehicles and all these. So we call this the far edge. So normally these areas, they are private. So in the sense that data can flow to the cloud, but normally does not enter. Okay. So this is not because just of a firewall. In fact, there are protocols that are used, such as OPC UA, that don't allow this without specific configuration. So in manufacturing, the manufacturers don't want a bidirectional communication necessarily. Okay. So, and this is an example where edge is important. So if all the data can be processed and controlled and stored at the edge, that's something that is important for manufacturing. And it's happening actually already today. On this example, what I bring you is the blue boxes, they represent parts of applications. Okay, so for instance, if I have an application that is monitoring the temperature in rooms, then that application, as you know, normally is possibly know, is containerized. Okay, so that's what we do today. We have maybe a container, a Docker container, to support the protocol that does the communication, okay, OPC-UA, MQTT. We have a container that can give basic analytics. Maybe we have a container that handles with TensorFlow, some aggregation of data, something like that. And the deployment of those containers today is orchestrated by, let's say, so a system, okay, that is a manager that decides where to place these, we call it microservices, so these containers. And as you possibly also know, so an example of such a tool that everybody's using is Kubernetes. Okay, so that's what Kubernetes does. Kubernetes knows about the nodes where we can place applications or containers that belong to an application, and does a decision on where to deploy those containers based on the need for CPU and memory. But Kubernetes does not care about the network. Okay, so Kubernetes does not know if it's deploying so two elements that need to be close together and have a minimum latency of 10 milliseconds to run together, okay, for instance. So, but basically what I'm also showing you is that these microservices are not anymore just computed at the cloud. They are actually being placed on different areas of this continuum, so edge to cloud continuum. And this notion of edge to cloud continuum has to do with computation. Okay, so we have two worlds, the networking world and the computational world sort of colliding. So here you have an example, for instance, for the same aspect, but for consumer IoT. So this could be, for instance, in a city where we have some buses with some edge nodes. Okay, so these are, as you know, could be simple nodes embedded like a Raspberry Pi. That's what is happening today. Could be something more clever like a regular laptop, which runs already some information. For instance, imagine on this bus, there are a number of users that sense information, take pictures, see the status of the road, write notes on about delays, and then that information is normally would be sent all to the cloud. And what is done today already is that data is aggregated on these yellow boxes, so on the edge, and then it's only processed to the cloud whenever required. And so this means that we reduce latency, or at least intuitively, we can reduce latency, and we also reduce potential costs because we don't need to pass all the information to the cloud. Okay. And so one thing that is happening on this edge cloud continuum, so the basis is our internet, is actually that this is continuing to change. Okay. So right now we still have, let's say, this notion of Internet of Things, but still static. Okay. So the routers are static. So in the core, most of the things are still static. But now there are new things becoming integrated. For instance, as you know, we have satellites. Satellites gives us great access to remote and large regions, as you guys have in Brazil, and they are mobile. they can route information. So today we have already the possibility to do routing, okay, on Leo constellations. So this means that these are edges, and we will have to deal with this integration on the internet. Okay, so this edge to cloud continuum will soon start to be very mobile and is already also in space. Okay, so it's a major confusion, let's say. So in order to ensure that we can, let's say, manage all this deployment of applications in this edge to cloud continuum, we have to evolve a little bit the systems that we have and were created more for cloud. Okay, so all the systems that we have and where we place our applications today, so Docker-based applications, they were developed for the cloud, and now they have to be adapted to this edge to cloud, where the microservices of applications can be deployed anywhere to serve specific requirements that an application has, like latency or bandwidth or cost, but also to serve preferences of the user. The user may say, I don't want my data, for instance, imagine in health, to really go to the cloud. I want it to stay on my edge, my home, for instance. And so in order to articulate this, we need, let's say, a knowledge plane or some tool that can do better articulation. And on this slide, you have a summary, which you can check after, of this part, okay, about what we need to make this, let's say, edge to cloud continuum really work. And I would say that from my side, and in addition to AI that we are all speaking about, right, and the role of generative AI, etc., what I think that is extremely important is to ensure that we can find a way to develop architectures that do joint computation and networking. And so John Gage, okay, said a long time ago that the network is the computer. And that is actually, I would say that the internet now is the computer, okay? So it is happening more and more and more with a lot of our efforts based on human configuration. Um, so in order to advance this, okay, so there are a number of challenges, and the next two slides. So I'm going to go a bit faster over this because I would like to give you an example with this code echo about how this orchestration can be done. What does it mean? What do we need? So there are a few challenges. Okay, so if we want to advance to this edge cloud continuum that will have large scale, very dense areas of very small and dumb sensors, and then also have to handle already clever sets of satellites and devices on the air, plus our personal devices that are increasing their intelligence. There are a number of challenges that we have to address in computer science. And from our perspective, okay, here in my team and my view is that there are much more challenges, but these are the ones that we are focusing upon. So joint computation networking to us is crucial, ensuring that whatever we do, even AI, if we need an AI system, it can run on top of mobile systems, not necessarily cellular, but I'm saying where routers may be mobile, where not just our end user devices are mobile, and context awareness. So bring some information about the user, about the application, and about the surroundings where the application is running. And so for that, we have a number of topics that we are working. And so today, Codeco, this project that I'm going to speak about, gives you an additional, more hands-on insight into the first topic, which is this flexible to edge cloud continuum, where we are trying to create a framework that not only is more flexible, so allows to support mobile environments, but actually brings resilience. And one of the let's say on this orchestration, on this management, one of the goals that we have is to reduce the energy that is required to do the orchestration. Okay, so another is of course improve latency or increase throughput, but we are also very interested in reducing latency. So this project, as I explained, is a large project so we have a few of these. You possibly also, I believe there are also common projects between Brazil and Europe. I also have some students there. But basically this is a large project involving 16 partners now across Europe. You have the logos of the main ones there. And where we decided, so based on this vision that you see and that we have in Fortis, we decided together, okay, to create an open source framework. Codeco means cognitive decentralized edge to cloud orchestration, that has the difference of trying to inject into this orchestration data metrics, compute metrics, which means observation of CPU and memory, and network metrics, which means observation of parameters such as latency, but also bandwidth, congestion, etc. And the reasons why we decided to do that, so the challenges are the ones that I just explained. And so what is the status of this? This project has already 1 year of living. In June, actually, will be 18 months. And we have already some code released, which you can play with. I will explain also in a bunch of slides. But more importantly, we will release the full framework, all components in June. So in this project, we are trying to orchestrate the edge to cloud continuum. But of course, because this has to be a bit more practical, we selected a number of use cases. So today, let's see if I manage still to speak about one, but you have here examples. So you have uh, the use cases that we are doing, okay, and you also have information, and there's a report that explains all this. So, but let me then go to the notion of orchestration, still from a high level perspective, but to give you a view. So basically, of course, when we go from idea, right? So this edge cloud continuum, we need to manage it. How can we do it? How can we work the computation layers, okay, plus the networking layers all together, because these are normally separate worlds in computer science. And then what to use in practice, okay? So what we decided to use was to create this framework around Kubernetes. And why? Because, as I explained, most of the IoT applications, industrial IoT applications, they are containerized today. We all use Docker, even for fun. And so this means that Kubernetes is the manager that handles how these microservices will be deployed. And so what we decided to do was to create a framework so framework means a set of software components that can work with Kubernetes. So they are modular, some are independent. Okay, so for instance, we have a scheduler. It can be used instead of the Kubernetes scheduler. We have an orchestrator based on AI. It can be used together with Kubernetes, not necessarily with our scheduler, but it is also intended to be worked as a whole. And the key aspects you have here. So this framework, where does it run? So here you have a representation, for instance, two edges, and I'm just giving you a high level example on how this would work. Okay, so this means, for instance, imagine that on edge one, I'm running some application. Okay, so this could be again, to make it simple, observation of people, so meaning the number of people in a building or in a room, okay, or could be environmental observation. And let's suppose that that service is running on Edge 1, and now there's a bunch of users moving more to Edge 2, okay? And basically, Codeco can be placed in the edge, can be placed also on the cloud. So here, this representation does not mean that Codeco necessarily has to run on the cloud. And basically, what it can do is based on some external injection of parameters. External here means, for instance, user moved or 10 users moved. So in fact, we should activate the service that was observing the room in Edge 1, in Edge 2, because now we have not many people there, or maybe it is empty, or maybe it is night. So these are external notions of context, okay, context awareness. And we want to activate that service on the second edge, okay? And then the service starts running, and all the, let's say, all the networking interconnections and the computational aspects have to be adapted. And that's what Codeco does. Codeco does that adaptation smoothly, or we hope it will do it smoothly. So, so then what does this project have? So in order to create this notion of orchestration, we decided, as I said, to create modular components, and you have here some examples. So for instance, we start, you see here the user. So the user is, for instance, a person that wants to deploy an application. So imagine you want to run some application with a mobile robot, okay? So with some friend, and that mobile robot uses Slam, okay, which is extremely heavy. And So the first aspect is normally when we work this today, we upload the application somewhere with Kubernetes. Okay, so for instance, we do it in Docker Hub or we use some other tool. And then we just say, okay, I need this CPU, I need this memory, and I want to run this for 100 days. Okay, and Kubernetes does wonders and basically places things in specific nodes. But in terms of the network, as I explained, there is no realization of what is going on. So maybe the node files or the link files between the nodes, and therefore our application cannot run. Kubernetes does not see that. So what we do with Codeco is that, so we have this interface to the user, and as you see here, there is here something called K8s control plane. So this means here we do a link to Kubernetes, and then we have a number of components that do different things. For instance, MDM can inject data observability to the system. For instance, it can say that the database has gone stale, database of the application. So imagine there was a problem with the database, with some data sources, and it went stale. Or actually that it grew too much, okay? And we need another node to run the application or to place the database. We have also the brain, let's say the orchestrator, that relies on AI to analyze how stable is the system over time. So this component that we call PDLC, it does not decide where to place the application. It simply tells the scheduler of which is the entity responsible to place the application or its components on different nodes. Okay, so imagine a graph and nodes, and the scheduler decides on how to do that. So PDLC tells the scheduler, hey, I think that the best option to run this application based on prior learning, okay, is actually to deploy it this way. But the scheduler makes the final decision on how to do that. We also have, as you see here, we inject some network information. Okay, so we bring some information, so for instance, bandwidth, congestion, but also other interesting things. For instance, energy spent on the connections or on the transmission on a specific node to adapt the orchestration. And so what is the status of this? And now I'm going to jump. You have a much more slides. So as I said, you have, if you want to read more, okay, about how does this work and what exactly this is, we have two large reports and also some papers, okay? So we collect everything on Zenodo, which is an international database, open. And here what you have is the architecture of Codeco, so meaning the software part. What exists already as open source is in green. What is still not uploaded, so one thing I did not mention is that Codeco is in an Eclipse repository. What is still not available is in red, but until June there will be a version available. And so I'm going to jump over a few slides, okay, because I would like to go to the use cases, but on these slides, you have more information about each of these components if you want to understand more what we do, okay? You also have some examples of metrics. So I'm speaking about metrics and data, but what exactly do we use? And you have here, okay, so for instance, data observability, we collect information about the databases, the freshness, compliance. So whether, for instance, in Europe, we are all into this GDPR and data protection, and therefore sometimes we cannot run applications outside Europe. And therefore, this is a notion of compliance, for instance. But we also collect some other information, okay, which you can see here. And I think the most interesting, and which is the one that we are still not yet completely integrating, is actually some information about user preferences. Okay, so this could be very simple examples, for instance, of location, not personal location. Okay, so this would be obfuscated marked location, so just points and nothing personal here. It's more about preferences. For instance, as I said, it's different if a user is running an application that while the user is running, right? Imagine some Google glasses and you are getting some information that you are running. It's completely different to do that while you are running than to do it while you are stopped. And so Codeco can take into consideration some of those metrics, okay? So now I'm going a bit faster, okay, because I would like to close in 3 or 4 minutes. So as I said, we have a number of use cases. So in the use cases, what we do is that we um, try to create, right, an environment that we thought was meaningful for Codeco to show how Codeco could perform and why we need something like Codeco. And we have 6 use cases, very different. So take a look because they are interesting and there's a lot of information already about them. The status of development of this is that right now, most of the use cases have already equipment set up and installed at a lab, okay? But now some of them are starting the second phase, which is integration in operational environments. And for instance, one of them that I bring to you is from University of Göttingen, being done with the city of Göttingen, where the colleagues are deploying using edge computing. And here, for instance, you see, okay, so there are some locations in the city and what they want to do. So they already have an edge node that senses some information. They also use lidars to understand traffic patterns. And here they give a very, very simple example, okay, of what happens. For instance, they have some locations around the city. Each of them includes 2 to 3 nodes. We call this a cluster, okay? And they are processing data. And maybe in some cases, it would be best to redistribute that processing. And for instance, an example very simple that I give here is, for instance, at night, where we have a direction of traffic with a lot of heavy traffic. And in fact, we have maybe on the other side, some edge node co-located with cameras processing barely nothing. And so in that case, some of the processing should be passed to the edge nodes that are almost empty. And that's where Codeco enters. Okay, so Codeco does not play with the application, does not even know the application. Okay, so the application is like a black box, but it can pass part of the application and information, so database status, to other nodes to redistribute the load, to reduce the energy that we need, to reduce the latency that we need for the specific application. So I'm now going to jump across the others, but as you see, you have some information about it, and also there are contacts around if you want to speak with the people. And I would like to call your attention, so these are last slides, to several things. So the first is that you can already, if you are interested on this experiment with Codeco, and we would be very glad if you would do so, because at different levels. So in the GitLab repository of Codeco, you have not only the components, but you also have information about how to run this. So you can just run it for the purpose of experiment, okay, really using the images that we have created, or you can really download the code, contribute, okay, and this is open source. So that's really a great world, open. So you have all the components of Codeco already with some parts. And then you also have something that we find very interesting, which is an experimentation framework that we are developing. So actually is led by our colleagues, Vastina in Greece, and they have developed really a pipeline for experimentation that you can do with Codeco. So this means you want to do some experiments, but you don't understand Kubernetes and you don't know exactly where do I get the data and how am I going to install Codeco and so on. And they have created a framework that you can just download and do some testings and develops everything from start to end. It has examples of applications. We have a data generator. Of course, as said, notice that this is our first phase of work. So not everything is perfect, but you can already experiment. We are doing the same and it works well. So meaning the experimentation framework, you have it here and you can see better. So there are also a few papers in Zenodo about this, about what we can do and what you can't do yet. At least you have already the new scheduler integrated. So this means that you can play with some applications and try to do a deployment, do comparisons with Kubernetes, and the experimentation framework does everything. So it deploys everything and does the collection of measurement parameters of all Codeco components. So it's very useful to play and to do some experiments and to write some papers. So you can also, final slides, promise 2 slides, so you can also engage with us. So as other projects, large projects, we have a program that is actually starting now, so it started in April, led by our partner Innova, and that basically is sort of an engagement program. So we are doing multiple events, you see there, okay, and we are going to give some awards. We also give the possibility to participate in some events, not necessarily just project events, but for instance, scientific workshops or conferences where the project is involved. So as you see there, okay, and So this is another way to get engaged. So this is my last slide. You have also all the links here. And I thank you for your time. And let's hear your questions. Thank you.
Thank you, Ruth. Very, very interesting stuff. I was already here browsing through your website, the open source repositories. As you know, I'm a big fan of open source, open research, and I think I will try to borrow some of your nice ideas in the project. I really like this packaging approach that you are trying out. I'm sharing here a little bit just about the project website. This program is also very interesting. This is a EU-wide type of initiative, so that they encourage all EU projects um, to do this IRCP program, to engage. It's very nice to see the maturity of how projects now are embracing open source in a much more, let's call it, effective and professional way.
Right.
Yeah.
I think that there's, as you know, Christian, a strong push, let's say, in Europe to do this, and across a lot of things, right? And I'm
Mhm.
very happy that we managed to convince even the large players in the project to open everything. Okay, so it was sort of a was an interesting process, I would say, but very happy for this. Okay, so everything is really open.
Thank you. A great example, and um, I'm sure we'll have opportunities to collaborate. Let me take one question from my side, which is related to one question that appeared over YouTube. Um, uh, First, I I must confess I was not aware about this fear. So this near and far cloud term. And I know you were working in user-centric. So for me, user-centric, near was like close to the user and farther from the user, but your perspectives are from the centralized operator cloud view. So near from
Exactly.
that and far from that, right? Just it's a matter of perspective, right?
Well, I mean, no, far is really considered end user, as close to the end user as possible. You are right, this is the telco perspective, but in fact is what is being used across all industry here. Okay, so meaning in Europe and even by, so let's say the European Commission, DG Connect, okay, for instance, far edge is really on the fringes, okay? So it is indeed there is an adoption of a telco centric, let's say, perspective. Okay, so not the
Uh-huh.
American folk perspective, but European telco perspective.
I will need to ask my colleagues that work here in Brazil what is our perspective. Maybe I can bring it to you what is far and near, because in Brazil, as you know, far and near and is also
Yeah, for instance, it's also, for instance, Huawei calls it here deep edge, I think, if I'm not mistaken, or I think
yes,
IBM
yes.
calls it micro edge, always the same, okay? So we're very similar. So fog is so there's also okay, but let's say, but this is indeed the approach being used.
Good to know. We need to we're always up to date. And one of the questions from Ariel was, is it the same as fog? Fog computing was a term that has already
Yeah.
some time. How do you relate fog? Fog would be the near edge, or
No, actually, fog is both, right? So you don't have it here, but fog, the concept of fog is more American, very interesting, okay, from I think Robert, right, from Cisco, not long time ago. And it's actually, so you know, we have these different views, and Europe is really more focused on boxes usually. But basically, fog is more variable, okay? So it actually covers far edge to near edge, but it's more flexible because it doesn't focus so much just on focus more on the functionality, on the functions that we have. So I would say that fog computing is actually the same thing, more or less, okay, with a bit more flexibility than far edge and near edge. So I think that the key difference here is that when we say far edge, there are a number of things that we cannot compute yet close to the data sources, okay? And so people in Europe are trying to do so to push functionality even from the network, so the aggregation, right, as far as possible to the data sources, and this is far edge, okay? So if we go to fog, so let's say less telco, more computational view, fog is more flexible, okay? There are also, so on the paper that this is a white paper, but you have information about that, about the different models, and also about origins of fog computing. There was something before fog computing, okay? So there are old ideas that anyway come to life, and what is happening now, okay? Or happened until 2021.
Mm-hmm. Good, good. Thanks. So I'm browsing here through the questions of the students that, as I explained to you, they do some homework on the topic of the seminar. So, and I spotted here a common type of questions around the security aspects. Here, one was very explicit here, asking what are uh, examples of security challenges. What are key challenges? Can you talk also exemplified? I know it's very much related to industrial use cases. So the are out there. So anyone in theory could have physical access. I guess that's a concern, or someone could pick up this device and then try to break it. Or what would you share about the security challenges?
Right, as you know, what happens now is that basically everything is very statically configured, okay? ACLs and service level agreements, and then also really hard, let's say, access to devices. So you mentioned manufacturing. No, there is no access to the manufacturing environments. They are closed, okay? They can send information. Nothing can enter. That's how it works today. So they can even disconnect if they want from the cloud because, okay, there's also possibly you all know, okay, so there's this notion of industrial edge, a big push from Siemens about equipment that is, let's say, a little scale lower than cloud in terms of computation and runs in the edges very well. There's all the processing. Now, let's suppose on this new environment, as you said, okay, where there is more flexibility, and now let's suppose if I can show you. So for instance, this kind of environments on the right-hand side, where now we have some manager, right? And we are orchestrating this edge to cloud. What are the issues that we have? So of course, as you know, some it's not that, for instance, a node enters. So for instance, with Kubernetes today, you have a list of suitable nodes, right? And those nodes, for instance, if you use AWS or whatever, okay, online cloud space, as you know, all the nodes are trustworthy for them at least, okay? But there are other problems. So one is being trustworthy, ensuring that's not a malicious user. That's how it is done today. But another problem, as I said, is compliance. Okay, can you run your data there? Can you run your application there? Okay, in your country, is it regulated accordingly to the rules of your country? Okay, so that's another aspect. Now, if we move to something where we need Codeco, okay, where more variable, and now a new node enters, like your smartphone, how can we know it's trustworthy? Okay, so there are several ways. One thing that we are looking into, okay, which I did not explain more technically, is that, let me just browse there. So I don't want to take a lot of time, but let me see, is here, is that on this orchestration and using AI and on the selection of nodes, we use something called, or we are proposing to use something called swarm computing, where the nodes, where we are going to, so the suitable nodes for this graph, okay, and to deploy the applications, they will set first some contracts, okay, based on DLTs, okay, so based on ledger technology. So to be more clear. So this means that before starting something, we are using smart contracts, okay? But of course, there must be some level so that there's one way. One is, okay, on my graph, I just use these nodes because I trust them. That's the normal way, okay, that we all do. Two, we now want really to use these more flexible structures. What can we use, okay? And one thing that has been used in the past, but we are not doing it, okay, is actually consider trust management as we do with humans. Okay, so it was quite used in opportunistic routing, for instance, where we negotiate trust or we have some rewards, okay, or some incentives for good behavior, so that this does not undermine attacks that we may have, but actually create systems that are more trustworthy. Okay, so for these decentralized systems, more flexible, decentralized trust management is something that would be relevant to consider.
Mm-hmm. Yeah. So
So for the
like
second part, which is attacks, okay, so somebody injects malicious information, may happen, okay, so your application runs like crazy, becomes greedy. So Codeco is prepared for that, okay, so we have sort of a governance and resilience framework that we are building, okay, but there's some rules so that we can test and prepare the system so that no application can do that, okay,
mhm.
but let's see if we are successful.
The other big thing before we finalize, that the time passes so fast. I was spotting here is as you put also in the title is energy efficiency. So we know sustainability is a big topic. There are so to say easier targets. So at device level, at compute level to do energy efficient aspects. What would you say it's the Codeco main goal or innovative approach towards energy efficiency or new insight or some insight that you are working on? What could you
Mhm.
share around it?
So I've so in this slide that you have, so what we are doing is, so notice that for us energy efficiency is not about the machines and making them work better. So imagine a graph where these applications are deployed. We are looking at the networking level and computational level, okay? So and what we are trying to say is that, okay, I'm going to select the graph, okay, the nodes and their interconnections so that it reduces the energy consumed. And we call that greenness, okay? And basically, let's say a user says, I want to operate my application and ensure that, I don't know, okay, I never reach 80% or of the full capacity of the system, or that I want to keep um, energy consumption on this level, okay? So in our case right now is really energy consumption. So battery of the nodes and energy used during transmission. Okay, but could be other things, could be CO2. We are not doing that yet. So, and what we do is we created some functions. Okay, so something that we use on the, let's say, on the orchestrator, on the AI-based orchestrator, which give a cost to a node. Okay, where that cost, the greenness cost of the node, relates with, let's say, the number of applications it is running and so on. Okay, the battery it has, and also with the transmissions that it's doing. Okay, so we have functions that you have here an example. Okay, so there's code also if you want to test, still very, I would say, initial, at least for the functions that we use, but you can play with it. So basically the idea is that, okay, so that's where we play with energy. So we are saying we select a graph where the nodes have a minimum energy cost, or where the graph has a minimum energy cost, taking into consideration other parameters as well. Okay, but so one thing we have to do is to prove that this is actually the best option. Okay, so right now this is like, let's say we are doing this because we believe it will improve overall the system, but we did not completely validate it yet. Okay, in large scale or something like that. Okay, but that's
Yeah,
the idea.
the energy domain is huge. It's I must say it's to embrace it as another research consideration. It's a big
Yeah.
challenge itself.
You have
And
a case of a use case, sorry to just add, about really energy, where colleagues from Universidad Politécnica de Madrid are
oh,
using Codeco, proposing to use Codeco to improve the smart grid operation. Okay, so
uh-huh.
you can check in the use cases.
Good. Yeah, yeah. I have some colleagues and background over there. So um, let me wrap up. First, of course, thank you, Ruth. It was great having your seminar, the open source out there. I will spread the word, and let's catch up more. And talking about catching up, let me just share with everyone what is coming next week. This is a topic you will certainly like, because it's related to industry, time-sensitive networking over wireless. So that will be next Thursday's seminar by Dave from Intel, and then we'll have an alumni from our faculty at Google working on Gemini, this generative AI work, and then we have others still for this first semester in our queue. So, Ruth, thank you again. See you soon. Keep
Thank you,
safe.
Christian. See you soon. See
Thank
you
you.
in the bus. Bye. Bye.
Bye. Thank you.